Hello all, this is Chandrakant. I have with me Eric Roston, who is also one of the co-authors of the paper. In this talk, we will be presenting our work on detecting images manipulated using a specialized technique called seam carving, and we have conducted this research at a small business organization, Maya Chitra. Seam carving was designed to be a content-aware image editing technique which could be used to reduce or increase image dimensions without affecting its salient contents to the maximum extent possible. But one could potentially use the same technique to remove objects from the images. Here is an example to demonstrate such a scenario. If we observe there are a set of buildings in the left image which are removed in the seam carved version on the right. This can be achieved very easily with seam carving. One can draw a removal mask to indicate the target objects to be removed. And then the seam carving algorithm can remove seams that will go through this removal mask. In order to make sure that image size is not modified, one can just insert the seams into the image and regain the original image size. That's how one can generate a manipulated image with minimal visual artifacts. This is the manipulated image overlaid on the seam removal mask, which indicates the regions of the image that are prone to seam removal. Here we are showing the manipulated image overlaid on the seam insertion mask, which indicates the regions of the image that are prone to seam insertion. Here is the actual ground truth seam mask. So in this paper, we have proposed a forensic technique that can predict these pixel-wise seam masks that can flag the regions of the image that are prone to seam carving. We also propose a new metric to better evaluate the localization capability of the detectors, and we also plan to release the datasets that we used for our experiments.
Hey everyone, Eric here. Let's look at the approach that we developed to detect seam carving. Initially, we trained a seam removal detector that accepts an image, in this slide a manipulated one, as input and generates a pixel-wise classification mask at the output using a unit-based architecture that utilizes an efficient net-based encoder. Similarly, we have a seam insertion detector which utilizes the same network architecture. And seam insertion detector outputs are fused into one image which we call the seam prediction mask, which comprises stage 1 of our approach. This seam prediction mask is then used as input to a second stage, which uses a ResNet-based CNN to perform a final binary classification as to whether the image given to stage 1 was seam carved or not. Finally, here is a high-level diagram of our pipeline with both stages shown. Here I want to briefly touch upon the ground truth masks used for training, in particular a seam removal detector. Since seam removal removes pixels from the input image, it's not immediately clear what we're actually trying to detect when we say we want to detect seam carving removal. In our formulation, we mark preserved pixel locations that were adjacent to removed seams as manipulated for our ground truth mask. For example, on the far left is an input image with its indices notated, and one seam that we'd like to remove in red. In the output image, we see indices which were not part of the seam preserved, while the ground truth mask is generated such that any preserved pixel location in that output image that was next to a removed seam is flagged. For seam insertion, the ground truth mask is simply marked with the locations of the inserted seams. In this slide, we highlight what happens when we remove a second seam right next to the first one that we removed. So in this case, notice that the ground truth seam mask is still 2 pixels wide, since we've actually removed some of the pixels that were previously adjacent to the first seam. And so these ground truth seam masks could even be improved further by taking grayscale values that represent how many seams the preserved pixel was adjacent to. But for this work, we've left the ground truth mask to be binary. And so the ground truth masks and input images are generated from 3 publicly available datasets. XView, XBD, and OrbView 3 datasets, which are varied but relatively high resolution satellite imagery datasets. To evaluate our stage 1 detectors, we employ modified versions of commonly used metrics such as accuracy, as well as the F1 score and Matthews correlation coefficient, which both take into account the inherent class imbalance in this problem. As scene carving typically removes a small amount of pixels, our ground truth masks will typically contain far fewer positives than negatives. So as probably known, the F1 score is 2 times precision times recall over precision plus recall, which is a function of the number of true positives, true negatives, false positives, and false negatives, while the Matthews correlation coefficient, which ranges between plus and minus 1, indicates none to complete correlation between the observed and predicted binary classifications. And so when we say a true positive, we mean that for a particular positive pixel location in the ground truth C mask, the same location in the predicted mask is positive, that is, they're pixel-wise. And so these two, along with an accuracy, again at a pixel level, are used throughout this work. A small modification is made here where when we calculate the number of true positives, we assign a true positive if our prediction is within a buffer of 1 pixel of a ground truth positive. This relaxation technique is similar to a metric used in evaluating road detectors, especially in the context of aerial imagery, and a representation of that is shown on the right here. And so to denote this change, we present the F1 and MCC scores with a -1 appended. Apart from these more standard metrics, we develop a way to measure how well our model localizes the seams of our ground truth mask, the seam localization score. While typical semantic segmentation problems use metrics such as the dice coefficient or intersection over union to quantify localization performance, such metrics are not as applicable to this problem, since the objects of interest, the positive classification regions, the seams, can be as small as 2 pixels wide and are highly sensitive to the metrics I just mentioned. So in some words, the seam localization score measures in terms of pixels how closely our predicted seams are to the ground truth seams. The GIF shown in this slide shows a set of ground truth seams in red and a shifted version of a single ground truth seam in green, where we can intuitively see that the seam localization score for a shifted version of a ground truth seam is the number of pixels associated with that shift. Here's the full formula for the seam localization score, where we're summing for each row I the number of pixels away the closest predicted positive is to the ground truth. So specifically, S of I would be the column index for seam S at a row I, which is the first term. And it's also included in the second term, which is the closest column index to the nearest ground truth positive. And if there were no predicted positives for a particular row I, the second term is set to W, the width of the image. And this means that the SLS ranges between 0 and W for a single seam. Then to compute an image level score, we simply take the seam level SLS and normalize it by the total number of seams. Here we show the performance of seam removal detectors with the various encoder backbone architectures, which give a good idea of the types of ranges to expect from the seam localization score, as well as the F1 score and the MCC1 score. These models are trained and evaluated on our XView dataset. We can see from the table that the seam localization score correlates quite well with the F1 and MCC scores, while noting that efficient EDB7 gave the best results across all 3 metrics.
So let me present few qualitative results of our method. Here is a manipulated image that we have shown earlier, if you remember. Here is the prediction mask generated by the seam removal detector. Here is the prediction mask generated by the seam insertion detector overlaid on the manipulated image. This is the predicted seam mask, which is the fusion of the outputs from 2 stage 1 models. When we compare it with actual ground truth mask, we can observe that models are almost accurate at flagging the manipulated regions. Seam carving can also be used to dislocate targets in an image with minimal visual artifacts. Here is an example where the object dislocation is done using seam carving. This is the manipulated image. This is the pristine image. This can be achieved by just removing seams on one side of the target and inserting them on the other side. Here is a quick comparison between the predicted seam mask and the actual ground truth mask. So it is critical to ensure that satellite images are not manipulated using techniques such as seam carving. And also, if an image is seam carved, we should be able to understand the intent behind manipulation. That is the primary motivation for developing the localized seam carving detectors. It's because the seam prediction masks that are localized at pixel level can expose manipulators' intention. For example, here are some sample seam carved images after object displacement. We can see that the seam prediction masks by our detector on the seam carved image look like this, and one can easily understand that the manipulator's intent is to displace objects by looking at these seam prediction masks. This is because removed seams are on one side of the image and inserted seams are on the other side. In a similar way, localized prediction masks can expose if the manipulator's intent is to remove objects from the image. For example, here are the pristine satellite images with removal masks overlaid on them. These are the seam-carved images with objects removed. And if we visualize the seam prediction masks after object removal, we can see that seam removal mask is converging to narrow necks. If we remember, these narrow necks are actually located exactly where the objects were removed, these necks. So it is very important to have a localized seam carving detector in addition to having the image level classifier.
The level of manipulation clearly depends on how much we're actually seam carving our images, and we'd like to see how our model generalizes across different seam carving ratios. To build some intuition, I have an original pristine image at the top left here, while I also have the 2%, 10%, and 50% seam carved versions, along with their ground truth seams in the bottom row. We see that at 2%, the seam carving algorithm is looking to minimize the distortion of buildings in the middle, opting mostly to take from the sides. While as we get to 50%, there is really no more room to take seams without altering the semantic content of the image. In this slide, we have both seam removal and insertion efficient net-based detectors that were trained with 10% seam-carved images from the XView dataset and evaluated on XView test sets with a variety of seam carving percentages, along with the stage 2 accuracy, which is computed using a single XView trained network. This shows that although we're varying the seam carving percentage significantly, the networks generalize the flagging manipulation quite well, with the stage 2 accuracy above 99%, regardless of the seam carving ratio used. However, the SLS, along with the MCC1 score, highlight the difficulty in localizing the seams at extreme levels of seam carving. It can be seen that they start to degrade quite heavily by 40% seam carving and poor performance at 50% as well. In particular, the SLS metric tells us that on average for 50% seam carving ratio, we are 21.79 pixels away from exactly localizing a given seam on average. These results indicate that although it is quite easy to detect a heavily seam carved image, it is much harder to actually localize the seams. In this case, since our evaluated model is trained on only 10% seam carved data, it's likely that we're missing a large number of seams as the seam carving percentage continues to increase. On the other end, at a 2% seam carving ratio, we see that while the MCC1 scores remain quite high, this is because their invariant to which class is positive and there are a lot of negatives in each image at a low seam carving percentage. The SLS score slightly suffers as we need to exactly predict a small number of seams to score well there. And correspondingly, the stage 2 accuracy does decrease slightly as missing a few seams leads to a pristine prediction. In summary, we covered our method to perform localized seam carving detection, both for seam removal and seam insertion. We developed a specialized metric to evaluate such detectors and how well they localize seams. And we covered our unique large seam carving datasets, which will be released to the public. Thanks so much for listening to our talk. I'd like to acknowledge Professor Manjanath, Professor Shiv, Lakshman, and DARPA for funding this work. Thanks again.